Let's do two Hardy-Weinberg equilibrium problems. So we have this population, and we have 160 showing a recessive order. We have Hardy-Weinberg equilibrium. So what we're going to do is we have P plus Q is equal to 1, and we have P squared plus 2PQ plus Q squared is equal to 1. So first, we know that Q squared is equal to 160 divided by 2,500 because we have a recessive disorder. That means that this is equal to 0.064 for Q squared. So then we just take the square root of both sides. We get that Q is equal to 0.253. So we have Q, therefore we know that P is equal to 1 minus Q. So P is equal to 1 minus 0.253. So P is equal to 0.747. Now we have to find our carriers. We can find this by knowing that 2PQ is going to be our heterozygotes. So that means that we have to find the 2 times 0.747 times 0.253. So this is equal to approximately 0.378. So now we have to multiply that ratio of the carriers, 0.378 times 2,500, which is our total population, which will give us 945 carriers. Now, after this, we want to find our homozygous dominant individuals. So you have P squared is equal to 0.747 squared. So P squared is equal to approximately 0.558. However, that's just the ratio. We want to take 0.588, the ratio, and multiply it by 2,500 so that we can find the actual number, which is 1,395 homozygous dominant individuals. So now for our second question, we are going to have a population of 800 beetles has the following genotypes. AA is equal to 320, AA is 400, and AA is 80. So we want to find the dominant allele frequency, recessive allele, and calculate the expected number of genotype frequency under Hardy-Weinberg equilibrium, calculate the expected number of individuals for each genotype, and then determine whether the population appears to be in Hardy-Weinberg equilibrium. So first we had to find the total number of alleles. So we know that each beetle has 2 alleles. Therefore, we have 800 beetles, each of them having 2. We have 1,600 in total. So after this, we had to find all of our dominant alleles. So AA is going to contribute to capital A alleles, and then we have AA is going to contribute 1 capital A allele. So we have A, which is equal to 2 times 320 plus 400. And we also have A, which is equal to 640 plus 400, which we just got from this. So we have a total of 1,040 A's, and we can find that P is equal to 1,040 over 1,600, which is our total. So P composes 0.65% of all of our total alleles. So after this, we can find our recessive alleles by taking the fact that AA is going to contribute 2 lowercase a alleles, and we also know that AA is going to contribute 1 A allele. So you have A is equal to 2 times 80 plus 400. So this is going to be 160 plus 400, and this is equal to 500. So if you find Q, you are going to take this 500 presents, and you're going to divide it by your total 1,600, and you get that Q composes a ratio of 0.35. So if you know that P plus Q is equal to 1, we know that we have 0.65 plus 0.35 is equal to 1, and this makes sense for Hardy-Weinberg equilibrium. So after this, we can find our genotype frequencies. We know that we can get P squared first by taking our 0.65 squared, and that is equal to 0.4225. Now 2PQ component, that is going to be 2 times 0.65 times 0.35. Now this is equal to 0.455, Well, q squared is equal to 0.35 squared, which is 0.1225. Now we have frequencies, however, we need actual expected numbers that we will receive out of our population. We know that we have AA is going to be equal to 0.4225 times 800. That is equal to 338. We know that AA, this is going to be 0.455 times 800, and this is going to be 364. We know lowercase a is going to be 0.125125 800, and this is equal to 98. So we can see that these are our actual expected numbers. Now we can compare them to what we have for our observed. Well, observed versus expected. Observed for AA, and lowercase aa, we have 320, we have 400, we have 80, and then here we had 338, we have 364, and we have 98. So we can see that they're not exactly, so the population might not be in perfect Hardy-Weinberg equilibrium. Now, you might use a chi-square to test if the difference is statistically significant.